So can anyone confirm? Am I audible? Hello. Can anyone confirm? Is my screen visible or not?
Yes, sir.
My screen is visible to you, no?
Yes, sir.
Okay, thank you. Okay, so let's start. Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL TA for the course Introduction to Probability Theory and Statistics. This course is offered by Professor S. Dharmaraja. He is a professor in IIT Delhi. Okay, so this is a 12-week course, and we are currently in the 11th week of the 12-week course. So that means it is the second last week of our course. Okay, so up to this point, we have like this course has mainly two parts. The first one is Introduction to Probability. And the second was in Statistics. Okay, so in Introduction to Probability, we have completed 8 lectures. Okay, 8 week for the intro probability, in which we have discussed about the basic concepts of probability and the different aspects or concepts used in the probability theory. And from ninth week onward, we discussed about statistics. Okay, so like in the ninth week, we have discussed about descriptive statistics. Okay, and we have also discussed about sampling distribution, in which we like discussed about T distribution, chi-square distribution, and F distribution. In the last week, that means in the 10th week, we have discussed about point and interval estimation. Okay, point and interval estimations. Now in the 11th week, we will mainly discuss about the testing of hypothesis. Okay, this is also like one of the statistical inference. Okay, one of the method to draw inference from the sample or from the data. Okay, in which we have discussed, we will discussed many things like what is hypothesis. Okay, and non-parametric statistical test is also like we will discuss today. Like goodness of fit test is there for we're using the chi-square distribution or chi-square test or distribution actually. We will also discuss about the different aspects of the testing of hypothesis like null and alternative hypothesis, also simple and composite hypothesis. Then we will discuss about Neyman-Pearson lemma and the test for the population mean, variance, and the distribution. Also, regarding the contingency tables, we've also discussed the test regarding the contingency tables as well. Okay, so these are some of the topics we will discuss in testing of hypothesis. So let's start with the hypothesis. Okay. So what is hypothesis? Like in statistical inference, if you people remember, let me. Uh, these are mainly categorized in two parts. Like the one is estimation part, and the second is testing of hypothesis. Okay, and again further, if we divide the estimation into more categories, like the one is the point estimation and the other one is the interval estimation. Okay, so till date we have discussed about the point and interval estimation in the previous week. Okay, now we will discuss about testing of hypothesis. Okay, these all are comes under the statistical inference. So that means, for example, suppose we want some parameter, some value of the parameter. Okay, we want to estimate that value because that's a very large population. And in general, in statistical inference, in classical models, usually the parameters are unknown but constants. So it is like not known prior. Okay, so we need some samples or data to estimate those unknown parameters. Okay, so these can be estimated in two different ways. The first is either estimate via assigning or estimating a single value, that is under the point estimation method. And there is also one way in which we give a range of values in which the true value, the true parameter value lies within under at certain confidence interval. Okay, so that we have discussed. Now we have the another one, hypothesis. Hypothesis is like some statement, some statement regarding the parameter of a distribution. Okay, parameter related to the population, or we can say. Okay, so this is the hypothesis. In first and second, we have a value, either a fixed value, a single value, or a range of value by which we estimate the parameter. But in case of hypothesis testing, we make an assumption or assertion. Okay, we make a statement that this parameter has a value this, and then we will check whether that particular hypothesis or particular statement is true under at certain level of significance or not. Okay, so this is called the hypothesis or testing of hypothesis. Let me write here. Okay, so hypothesis is like the statement, a statement which we made with respect to the population, with respect to the population is called hypothesis. Okay, so some statement or some assertion that we made with respect to the population or the factors that influences or describes the population, that is the parameter as well. Okay, is called the hypothesis. Okay, and this the statement can be either rejected or accepted based on the test, based on the process or algorithm that we will follow. This process is called the testing of hypothesis. We use some sample values, and by the help of that sample values we make a decision, either we reject that hypothesis or accept that hypothesis. Then this process is called testing of hypothesis. Okay, now there are mainly two kinds of hypothesis is there actually. The first one is like there are two types of hypothesis. The first one is null hypothesis, and the second one is alternate or alternative sometimes also used. Alternative hypothesis. Okay, so these hypotheses is defined like this: the statement about an unknown parameter, like statement about an unknown parameter theta which belongs to the parameter space theta, capital theta, is called a null hypothesis. By null hypothesis denoted by this null hypothesis is mainly denoted by H naught such that theta belongs to capital theta naught. Okay, where capital theta naught is a subset of the parameter space theta. Okay, so this is called the null hypothesis. And the complement statement of this particular hypothesis is called the alternate hypothesis. And the complement statement is called the alternate hypothesis. Okay, so and it is mainly denoted by H1. Usually H1 or sometimes HA also is there, like H1 or HA. Okay, so we will use like H1. So theta belongs to capital theta 1, which is nothing but capital theta and difference of capital theta naught. Okay, so the statement about the unknown parameter is called the null hypothesis, and the alternate or complement statement is called alternative hypothesis. Okay, the null hypothesis is denoted by H naught and the alternative hypothesis is usually denoted by H1. Okay, so there is one remark. A points like need to be kept here, like that the equal to is always included in the null hypothesis. Okay, so like that equal to is always included in the null hypothesis. So whenever we define or construct the hypothesis, then always we will try to include the equal to sign in the null hypothesis, and then not equal to or greater than or less than will be there in the alternate hypothesis. Okay, so this is mainly two type of hypothesis. Also, like on the basis of the nature of the hypothesis, there are two different kinds of hypothesis is there, like on the basis of the nature of these hypotheses, we have like simple and sorry composite. Composite hypothesis. Okay, So we have simple and composite hypothesis. So let's define these as well. The hypothesis, like is said to be simple if both the capital theta naught and capital theta 1 consist of only 1 point. Okay, when it contains only 1 point, then it is said to be a simple hypothesis, or like any hypothesis that is not simple is called composite hypothesis. Okay, so a simple hypothesis is that type of hypothesis in which the parameter space has only 1 point. So in other word, we can like say that in other words, like the simple hypothesis describes the parameter entirely, parameter or population, we can say, entirely, but the composite hypothesis like does not describes the whole parameter, or this can be like, for example, suppose we have h naught such that mu equal to, mu is any average value, mu equal to 4 against h1 such that mu is not equal to 4. Okay, so here like here this one, this describes whole or entirely that the value of mu is 4. So this is a simple hypothesis. And the another one is like this is composite because it tells us that mu is not equal to 4. That doesn't mean like it may possible mu is more than 4, mu is less than 4. So it is not like fully describe the uh, parameter. Okay, so in that case, it is a composite in nature, or the simple one is equal to, clear. Okay, so these are the null and alternative hypothesis, and then simple and composite hypothesis. Now, the next topic is test statistic. Okay, so we have already discussed about statistic. Okay, statistics are the functional form or the functions of the random samples. Okay, a functional form that will be constructed with the help of random variables or random samples. Okay, so those statistics that are used uh, in like in point and interval estimation, we have used different kinds of statistics. So those are estimators. Okay, now the statistic here which is using like which is used to test the hypothesis. So that's why it is called test statistics. Okay, so a test statistic is a statistic as well. A test statistic is a statistic whose values determine whose values determine using the realization of the sample. Like as we know that statistic is a functional form or functions of random samples. So the test statistic, the value of the test statistics actually vary on the basis of sample to sample. Here, since we use the test statistics because that statistics is used to for testing purpose actually. So the test statistics is a statistics whose value is determined using the realization of the sample. That means that sample, it depends on the sample actually. Okay, so we have discussed different test statistics under different scenarios. Okay, now the next topic is critical reason. Okay, so critical reason, the critical reason, it is also called like the region of rejection. Okay, it is also called the rejection region. Okay, is the set of values, is the set of values of the test statistics, test statistics for which the null hypothesis is to be rejected. Okay, so set of those values for which set of those values of the test statistic for which the null hypothesis is rejected is that those samples or those reason are termed as critical reason. Okay, so now we have one more like additional terminology. There are two kinds of error exist in the testing of hypothesis actually. So those are called type 1 error and type 2 error. So okay, let's start with the errors. Okay, so there are two kinds of error. The first one is type 1 error. Okay, so type 1 error is usually denoted by alpha. Okay, and it is defined as the probability of like rejecting H naught, rejecting the null hypothesis when H naught is true. Okay, so if H naught is true, then we need to accept that. But due to some error, we reject that H naught or we reject the null hypothesis, then this is a kind of error. So this type of error is termed as type 1 error. Okay, usually denoted by alpha. So the probability of rejecting the null hypothesis when it is true is called type 1 error. Okay, like similarly, type 2 error is also there. Okay, so type 2 error is mainly like denoted by beta. So beta is type 2 error, which is defined as probability. The first one is rejecting H naught. when it is true. So the second one is accepting H naught. So accept the null hypothesis when it is false, when H naught is false. Okay. So since the null hypothesis is not true, but still we accept the hypothesis, so it is the second kind of error and termed as type 2 error. So it is denoted by beta, which is probability of accepting H naught when H naught is false. Okay. Like there is one more topic. This is called power of a test. Like we like perform the testing of hypothesis. Okay, so different test has different powers. Okay, so we need to check which test is more powerful as compared to the other. So that can be like test check with the help of power of a test. It is nothing but the 1 minus beta, that is 1 minus like probability of type 2 error. Okay, so when we need power of a test, so that means what? That means the more the power of a test, the less the type 2 error of that particular test. Okay, so okay, we have one question related to this type of errors. Okay, so let's start. Okay, like x is a random variable that follows exponential distribution. X is a random variable that follows exponential distribution with parameter lambda. Okay, now consider the following null hypothesis. Like we are given the null hypothesis H naught such that mu equal to 20 against the alternate hypothesis H1 such that mu equal to 30. Okay, now here mu equal to 1 by lambda, that is the average value, the mean is there actually. Okay, now let a sample of size 1, let a sample of size 1. So size 1, that is the singular value x is there. X is observed from the distribution. From the distribution, the test is to reject the null hypothesis. We are given the critical reason actually. Okay, so the test is to reject, like the test is to reject the null hypothesis if value of x is greater than 28. If value of x is greater than 28. Okay, so now we need to calculate type 1 error and type 2 error. We need to calculate type 1 error and type 2 error for this question. Okay, so let's start. Okay, so we are given here like x follows exponential lambda. So like the PDF of the random variable x is lambda e to the power minus lambda x, for lambda is greater than 0, x is greater than 0. And the CDF also, we can write the CDF. It is 1 minus e to the power minus lambda x, for lambda is greater than 0, x is greater than 0. Okay, so also we are given here like the hypothesis. In the question, hypothesis is given. Okay, we are given the hypothesis, the null hypothesis, mu equal to 20 against the alternative hypothesis, mu equal to 30. Okay, so we need to check this. So also like we are given the critical reason actually. Critical region is also called region of rejection. So that region in which we reject the null hypothesis. Okay, for which the null hypothesis is to be rejected. Okay, so when we reject the null hypothesis, we reject the null hypothesis if like here you can see the test is to reject the null hypothesis if value of x is greater than 28. So that means the critical reason is what? The critical reason is x is greater than 28. We can write here capital X actually. Okay, x is greater than 28 is a critical reason. Okay, so we have all the information that are given in the question. Now let's start with first question. We need to calculate the type 1 error, which is denoted by alpha, and it is defined as reject H naught when H naught is true. Here, this parallel pi, the vertical line is when or given. Reject H naught when H naught is true. Okay. So reject H naught. When we reject the H naught, when the value of x is greater than 28, when the value lie with the critical region. So that means what? That means we can write like this, like x is greater than 28. In that scenario, we reject the H naught. Under what? When H naught is true. When H naught is true, the value of mu is what? Is 20. So we can write this in this form. Okay. The definition is reject H naught when H naught is true. This implies x is greater than 28 is the critical reason. So we need to calculate the probability that x is greater than 28 when H naught is true. That means when mu equal to 20. So under the condition that mu equal to 20, we need to find the probability that x is greater than 28. Okay, so it is simple actually. If you can see, x is greater than 28 is like nothing but 1 minus fx of x equal to 28. Okay, at mu equal to 20. Okay, so from here, we can write like e to the power minus 28 upon 20. Okay, now the value of alpha is 0.2466. You can solve this with the help of the calculator or some other software. You will find the value of alpha is 0.2466 or 24.66%. Okay. So like this is the type 1 error. Type 1 error is 24%, 24.66% type 1 error is there. Okay. So that means, sorry. So that means 24%, roughly we can say 24 or 25% the chances that we reject the null hypothesis, even if the null hypothesis is true. So this is the interpretation for the null hypothesis for the type 1 error. Similarly, we need to calculate like type 2 error also, which is defined as the probability that accept H naught when H naught is false. Okay, we need to accept H naught when H naught is false, or in better wording, if you can write, we need to like, since these are the sample properties, okay, on the basis of the sample, we draw these inferences. So we will like try to conclude these strong word. So instead of accepting H naught, we fail to reject. Okay. So like fail to reject H naught when H naught is false. Since it is based on the sample only. Okay. We have collected one sample and on the basis of that sample, we calculate the test statistics, and then with the help of those, the value of the test statistics, we make some assumptions, or sorry, we make some comparison with the help of the tabulated value and the calculated value, and then draw a statement, okay, or make any statement. So probability accept H naught or fail to reject H naught when H naught is false. So under the what condition we fail to reject the H naught? When the value of X is less than or equal to 28, because the critical reason is X is greater than 28 is the critical reason. So that means the value of X is greater than 28. In that scenario, we reject the null hypothesis. So we accept the null hypothesis when the value of X is less than or equal to 28. So we have put the value X is less than or equal to 28 under H naught is false. When H naught is false, then H1 is true, because that is the alternate. That is the alternate hypothesis. And we have also like defined here the alternate hypothesis is mu equal to 30. So that means we need to find mu equal to 30. Simple. That means what? We need to calculate the probability that X is less than 28, less than or equal to 28 under the condition that the value of mu is 30. So we need to find this. Okay, again, since it is nothing but the CDF, fx of X equal to 28 under the condition that mu equal to 30. So this is what? 1 minus e to the power minus 28 upon 30. Simple. So after calculation, you will find like the value of beta is 0.6088. Okay. So this is the type 2 error. That means what? 60% chances is there that we accept the null hypothesis, even if the null hypothesis is wrong. Okay. So 60% chances that the type 2 error like is like probably happen. Okay. Also, we can calculate the power of the test. Power of the test is what? It's 1 minus beta, the type 2 error. It's 1 minus 0.6088 actually. 6088. So it is like 0.3912. Okay. 0.3912 is this. Okay. So its power. So that means 39. We can say that. So it is like quite low number for the power of a test. So it is not a like good test. Okay. So this is how we calculate the type 1 and type 2 error. Okay. Up to this point, if anyone have any problem, then he or she may ask. Is it okay up to this point? No? Now the next is p-value. Okay. So like the p-value is what? The p-value is the probability of obtaining a result. It is defined as the probability of obtaining a result equal to or more extreme. Equal to or more extreme than what was actually observed. Okay. So p-value is the probability of obtaining a result equal to or more extreme than what was actually observed. Okay. This is the p-value, or we can say that the smaller the p-value, like the smaller the p-value, the larger the significance. Okay, so that is what is the meaning of significance? That is, we reject H naught if p value is less than alpha. That is what? Like we reject the null hypothesis H naught if p value is less than alpha. Alpha is what? Level of significance or type 1 error. Okay. So in that case, if the p value is smaller as compared to the alpha, then we reject the null hypothesis. Okay. The smaller the p value, the larger the significance. Okay. So this is the some terminologies we will use in testing of hypothesis. So now we have one lemma actually, one important lemma. Neyman-Pearson lemma is there. Okay. So Neyman-Pearson lemma is there. This lemma is mainly like used for simple versus simple hypothesis actually. Okay. Like this lemma is used for simple hypothesis versus simple hypothesis. Okay, so that means what? That means if we have alternate hypothesis in composite in nature, so in that case we can't use like we will not use the Neyman-Pearson lemma in that scenario. Okay, and this NP lemma, we in NP lemma we try to maximize the power of a test by minimizing the type 2 error. Like in NP lemma, we try to maximize the power of a test. Okay, that is by minimizing the type 2 error. The minimum the value of type 2 error, the more the powerful the test is. Okay, so NP lemma will reject the null hypothesis if the likelihood ratio is less than for the critical value. Okay, like we can write here actually like this. Like NP lemma will reject the null hypothesis reject the null hypothesis if the likelihood ratio that is L naught upon L1. Okay, that is the likelihood, the value or the functional form of likelihood at L at the like at the null hypothesis. Like okay, under the null hypothesis, the value of likelihood divided by the value of likelihood under the alternate hypothesis, and then the ratio. This is called the likelihood ratio. L1 upon L sorry L naught upon L1 and is less than a critical value. A critical value that is suppose for the k is that critical value, then the L1 sorry L naught upon L1, if L naught upon L1 is less than k, then in that scenario NP lemma state that we will reject the null hypothesis. Okay, now let me write the lemma. Okay, the structured lemma is also there. Okay, so like consider we have like consider the null hypothesis H naught, which is theta equal to theta naught, some particular value of theta, that is theta naught, against H1 such that theta equal to theta 1. Here, theta equal to either theta naught or theta equal to theta 1. Simple hypothesis versus simple hypothesis. So we can use like Neyman-Pearson lemma. Okay. Then any test. So suppose we have a test. Then any test phi of the form. Suppose like the first point is we have defined the phi function. Okay. It is a test actually on the basis of the sample. So it is either one if like f1 x divided by f naught x is greater than k, gamma if like f1 x divided by f naught x is equal to k, and 0 like if f1 x divided by f naught x is less than k. Here f1 and f naught is like the value of the function, okay, the PDF under H naught and H1. No, 0, H naught is like the under the null hypothesis and H1 is under the alternate hypothesis. Okay, so this test, then the phi test, then the test phi, which is defined as this test is the most powerful test. Of its size k. Here, suppose we have say that the size is k. Okay. Uh, like here the value of k is greater than 0 and is a constant. Okay, is a constant, and like the value of gamma lies within 0 to 1 excluding both, and like f1 x is theta 1 x. That means what? That means the f1 x is the uh, PDF under the alternate hypothesis, and f naught x is the PDF under the null hypothesis. Okay, so this is the first. When phi x is the most powerful test if this condition holds. And what if the value of k is infinite? So there is one more condition. If the value of k is infinity, then the test, like the test which is phi x is given two values, either 1 or 0. The value is 1 is given if like f naught x equal to 0, and 0 if the value of f naught x equals, sorry, not equals, actually this time it is greater than 0. So in this case it gives the value k equal to infinity. Okay, so this test is the most powerful test of size, is the most powerful of size 0, of size 0 for testing the null hypothesis H naught against the alternative hypothesis H1. Okay, so this is the Neyman-Pearson lemma. This lemma is mainly used for simple hypothesis versus simple hypothesis testing, and this is this gives the most powerful test under for the given size. Okay, this lemma gives the most powerful test under the given condition or given size. Okay, so we can solve some numericals on the basis of this lemma as well. Okay, now the next is the test for the population mean. Okay, now we will use the testing method to test the population mean. Okay, so test for the population mean, here we have options here. Okay, we have given some random samples. Okay, suppose we have x1, x2, xn are random samples from a particular distribution. Here we have considered the normal distribution. Okay, and we need to define the test statistics under the given scenario. Okay, and with the help of those test statistics, okay, we can draw inference. Okay, so let me define the test statistic first. Okay, so let or suppose x1, x2, xn are the random samples from a normal population with the mean mu and variance sigma square. Okay, uh, we are given this. We need to test the mean actually. So we have two conditions actually. Since we are going to test the mean, so we have either known value of variance or unknown value of variance. Okay, so let's start with case one. Okay, when sigma square is known, that is when we have known variance, then in that case, we define the statistics that is nothing but the z statistics, which is x bar minus mu upon sigma by root n, and this follows actually standard normal distribution with mean 0 and variance 1. Okay, so this is the test statistics when we are dealing the testing of population mean for the normal test, for the normal distribution when the variance is known. Okay, and the case second is also there. Okay, what if we don't know the variance? Okay, sigma square is unknown. So when the sigma square is unknown, then the sampling distribution of the test statistics is actually considered as t distribution. When sigma square is unknown, then the sampling distribution under consideration is like t distribution. Okay, so population variance is replaced by its estimate. Okay, so in that case the population value is replaced by its estimated value, that is the sample variance. Okay, so t is defined as x bar minus mu upon sigma by root n is there when sigma square is known, but since sigma square is unknown, so the estimate of sigma square is s. Okay, so s by root n. So this is the t distribution. Okay, or this follow the t distribution with n degree of freedom. Okay, now also we have one remark actually. Okay, we will solve some questions on the basis of these two, but let's first write the remark. Okay, if n is greater than 30, if the n value is greater than or equal to 30, then in that case, the T distribution can be replaced by the standard normal distribution. Then the T distribution can be replaced by standard normal distribution. Even like if you see the T table, then after the 30 value or after the 40 value, usually 30, but you can in some table you may get the T value at 40 degree of freedom. After that, we will follow the like normal table actually there. Okay, so that's why even T distribution is symmetrical in nature that we have already discussed in the ninth week. Okay, ninth week of this course, we have discussed about the T distribution, and there we have like see it is symmetrical in nature, and the normal table or sorry normal distribution is also symmetrical in nature. Okay, so this is the cases. Okay, so let's solve an example on this basis. Okay, so okay, so the question is like, assume that the exam marks of students follows normal distribution. Assume that the examination marks, okay, of students follow normal distribution with mean mu and variance sigma square with known variance actually sigma squared 0.25 is there. Okay, now test the hypothesis. Test the hypothesis. The null hypothesis is H naught such that mu equal to 8 against the alternate hypothesis H1 such that mu is not equal to 8. Okay, so this is simple versus composite hypothesis, if you can see. Okay, level of significance with level of significance 0.01, that is at least at means 1% level of significance, and the sample mean being equal 7.8, and the sample size is sorry, it's 50, not 150. Sample size is 50. Okay, so we are given the information. Okay, we are given the sigma square value, x bar value, the sample mean is there, the sample size is there. Okay, so let's solve this example. So like we are given n equal to 50, alpha equal to 0.01, x bar which is sample mean 7.8. Okay, sigma square is also there 0.25. Okay, so we need to construct the hypothesis. The first step is to construct the hypothesis, and the hypothesis is what? The null hypothesis is the parameter value is 8 against the alternative hypothesis. The parameter value is not equal to 8. Okay, the next step is to, on the basis of the test statistics, we find the test statistics value. Okay, so here since we are given the sigma square value. That means variance is known. So Z test statistics is defined here. Okay, so Z test statistics was x bar minus mu upon sigma by root n. We are given the values. Okay, so this is actually x bar is 7.8 minus mu. Since we are like what? We are discussing like under the null hypothesis. Okay, so that is 8. These are like under null hypothesis. We are testing the null hypothesis. Okay, so minus 8 upon the value of sigma is there 0.25. The value of sigma square is 0.25. So this implies the value of sigma is 0.5 actually. 0.5 and the divided by root n. The n is 50. So under root of 50. Okay. So if you can solve, it is minus of 0.2 and then divided by like the denominator term is 0. Okay, 0707. Okay, so after solving we will get z value minus of 2.83. Okay, so now the next step is we have calculated the z value. Okay, we can write it like z calculated, for example zcal for calculated. Okay, this value comes out to be minus times of 2.83. Now we need to check the value with the help of the table as well. Okay, so the next step is, so for z value at alpha equal to 0.01, okay, we will get like it is minus times of 2.58. Okay, so minus times of 2.58 is the value. Okay, here let me draw a curve actually. Okay, so these are the probability. Okay, these are the like these shaded region by yellow in color. So okay, so these are like what alpha by 2 and alpha by 2 is this. Okay, and these are the critical reason actually. These are the critical reason. So our value either lie in that reason or not. Since we have like okay, so we have like minus of 2.58 or 2.58. Okay, now we need to check the value that we have calculated. The calculated statistics value is minus times of 2.83, which is obviously beyond the or the left side of the minus times of 2.58. That means this test statistics lie in the critical region. And we know that the critical region is also known as region of rejection. That means if the test statistics lie within the critical region, so in that case, we reject the null hypothesis. Okay, so our conclusion is what? So our conclusion is like we reject the null hypothesis. Okay, and what is the null hypothesis? That means the value, the average value is 8. So we reject that value. So that means there is a significant option, like we can see that the value is not equal to 8. Okay, so the average value is not equal to 8. This is clearly seen. Okay, with the help of these sample observations. Okay, so these are the conditions. Suppose in a similar manner, if we haven't known about the sigma square value, then in that case we have the S square. The sample variance is there, and we follow the same process. And with the help of the T table in that scenario, we can conclude whether this test statistic value lie within the range or in the critical region, and we conclude our result. Okay. So the next is like test for the difference between two means. Okay, we have till that we have we have test for the single mean. Now here the test the difference between two means. Okay, so here we have again like H naught, that is the null hypothesis. So equality sign must be like included in the null hypothesis. So that means mu1 equal to mu2 or mu1 minus mu2 equal to 0 is there. Okay, or we can say the delta. Okay, we can say that the delta, if we can write equality sign is there, then this or delta. Okay, against the alternative hypothesis, mu1 minus mu2 is not equal to delta. Okay, so we can take the value of delta as 0 and here not 0. Okay, similar. So now the test statistics for the differences between two means is again the z statistic, which is x bar minus y bar minus times of like mu1 minus mu2 and divided by we have like sigma 1 square n1 plus sigma 2 square upon n2 is there. Okay, and this is the case one when like when sigma square is like known, but there is possibility that sigma square is unknown. Okay, so this is the case one. Okay, now the case is when sigma square is unknown, then again we use pooled sample variance. Okay, and this z statistics converted into t statistics and follows the t distribution. Okay, so then in that scenario the t statistics is defined as like similar manner x bar minus y bar minus of mu1 minus mu2 and divided by there is a sigma square is unknown, so we have a pooled variance. Pooled variance is denoted by like sp. Okay, this is a standard deviation. Okay, the square root of the pooled variance, which is 1 by n1 plus 1 by n2. Now where how to calculate the pooled variance? Sp square is n1 minus 1 s1 square plus sorry not plus actually n2 minus 1 s2 square and divided by n1 plus n2 minus 2, and this term follows actually t distribution with n1 minus n2 minus 2 degree of freedom. Okay, and this is called actually pooled variance. This is called pooled variance. Okay, and follow the this distribution. Okay, we have one question on the basis of this as well. Okay, so a nice question. Let's write it. The average return of a portfolio A the average return of a portfolio A of 10 stocks. Stocks was 77%. Okay, these are one information. Now, the average return of a similar portfolio like spatial balancing method is there. Okay, Okay, this portfolio is like use the spatial balancing method, means some other technique. Okay, to create the portfolio. Uh, okay, balance portfolio B of still there 10 stocks. Okay, was 75. Okay, so that means portfolio A has 77% and portfolio B of 10 stock was 75% return. Okay, carry out a statistical test. Carry out a statistical test to assess whether the portfolio with the spatial balancing method spatial balancing method, that is we are talking about portfolio B, has the same return as portfolio A at 5% level of significance. Okay, we need to check that. So these are the question. Okay, this is the question. We can use the test statistics here. Okay, we can use our this concept to test whether these two portfolios perform like equally perform, or there is a performance difference between these two portfolios. Okay, so we are also given we are given some values actually. We are given summation of xi from 1 to 10. Xi square is actually is 59,420, and summation of I from 1 to 10 yi square is 56,390. So these are the values we are given. Now assuming the returns are normally distributed, and variance of the underlying distribution for each portfolio is same, and the variance of the underlying distribution, sorry, for each portfolio is same. Okay, so these are given. Now we need to check the hypothesis. Okay, so for that purpose we need to first construct the hypothesis. Okay, so like the hypothesis is the H naught, that is both have the same performance. So that means mu1 equal to mu2, or we can say that mu1 minus mu2 equal to 0. Okay, and the alternative hypothesis is like mu1 is not equal to mu2. Okay, now the test statistics is, since we don't have the variance is unknown here, so obviously t is there. Okay, so it is x bar minus y bar minus times of like mu1 minus mu2 and divided by sp. It's not a square actually, it's 1 by n1 plus 1 by n2. Okay, we have the x bar, we have the y bar. Okay, so let me write here actually. The n1 here is 10, N2 here is 10 again. X bar is 77 because 77% return. So on an average, 77% return from the portfolio A. And Y bar is 75%. So that is XY bar is 75 is there. Okay. So putting these value, we can able to like calculate the SP. SP value is actually 3.873. These are like a lengthy calculation only. So I'm just writing the direct value. We're putting the values like we know that na n1 minus 1 s1 is square plus n2 minus 1 s2 is square and n1 plus n2 minus 2. Okay, so it's sp square actually. So from there only sp square is, if you can calculate, it is 3.873 whole square. So from here onward sp is 3.873. Okay, so we have SP, we have N1, we have N2, we have X bar, we have Y bar. Okay, and we have mu1 minus mu2. Mu1 minus mu2 under H naught is what? 0. Okay, so just putting those values. So like T naught for under the this, so 77 minus 75 minus mu1 minus mu naught, that is 0. It is 3.873 and under root of 1 by 10 plus 1 by 10. Again, we need to solve this. And after the simplification, we will find 1.15. Okay. So this is the calculated value. Okay. Now we need to find the critical value. Critical value. So for critical value, we need to first calculate the degree of freedom, which is n1 plus n2 minus 2, which is 10 plus 10 minus 2 comes out to be 18. So the t value at 18, and we have the level of significance is there in question or not. We are given 5% level of significance. Okay, so you can check the value at 5% level of significance at degree of freedom 18. Uh, we may find the value from the T table is 1.738. Okay, so here you can see that like if we can like make a graph, since the T distribution is always also symmetrical in nature. So we have 1.738. Okay, so suppose this is 1.738 and the calculated value is 1.15. So obviously 1 point, suppose this value. Okay, so this is the 1.15. Okay, so obviously this is not lie in the critical region because this is the critical region. Okay, and this value, the calculated value, is not lying in the critical region. So that means what? So that means we can conclude that we fail to reject the null hypothesis. So we conclude that we fail to reject the null hypothesis. That is the null hypothesis we are not able to like fail. That is accepted in English or in general terms. So that means what? Both the stock or both the portfolio perform, both the portfolio has a same performance level. Okay. So this is the question, and this is how we use the testing. The mean testing, the difference of mean testing, the single mean testing is also there. We can use these in our day-to-day like life. Okay. Now we have the test for the population variance also. Up to this point, we have derived the test for the mean. Okay, for the single mean and for the difference of mean. But now we will define the test for the population variance. Okay, so the test for the population variance, again here like let we have x1, x2, Xn are random samples. Random samples from normal distribution with mean mu and variance sigma square. Okay, here. Okay, now we construct the hypothesis, the null hypothesis H naught, which is sigma square is equal to some particular value sigma naught square against the alternative hypothesis sigma square is not equal to the sigma naught square. Okay, so this is the hypothesis. So for under this condition, we define the test statistics like this: n minus 1 s square upon sigma square. This follows chi square with n minus 1 degree of freedom. Here s square is 1 upon n minus 1 summation of xi minus x bar whole square I from 1 to n. Okay, and this is called sample variance. Okay, so this is how we use the chi-square. So for the testing of the population variance, we use chi-square statistic. Okay, chi-square test is there. Chi-square table we will use for the critical value. Okay, also we have, suppose in case we have two independent population. Okay, since there is no mean value involved in this, so we don't like use the when mu is known, when mu is unknown. Okay, so this is the only case for the single parameter, sorry, for the single population. Now for the double population, now what if we have double population? Now two independent population, so let's consider like two independent population with known means. With known means, that is, let's assume mu1 and mu2. Okay, but unknown variances. Unknown variances, suppose sigma x square and sigma y square. Okay, so we have like the null hypothesis again. Uh, in that scenario, we have two independent population with known means and unknown variances. We need to check the variability about the variability of these two populations. So the first one, like we need the first step is to construct the hypothesis. So the null hypothesis is like what? The variability, the variability of these two independent population is same. Okay, the variability of the two independent population is same. So that means sigma x square equal to sigma y square against the alternate hypothesis sigma x square is not equal to sigma y square. Okay, and here if you can, like, since it follows the chi-square na, so we have like some other statistic that we will discuss during the numericals. Okay, so we have one question. Okay, I'm not writing the whole question because it's a very long question, but I can like read the question and write the those values, okay, that are given. So Chicago Mercantile Exchange is one of the largest future and option exchanges. Okay, it is a dominant venue for the sale of gold future contracts. Historically, weekly return of the futures have a standard deviation of 0.4. Okay, so we have a like what? We have a standard deviation of 0.4%. Okay, A trader wants to verify whether this claim will still adequately describes the standard deviation of the contract. Okay, so these are the past record shows that the standard deviation is 0.4%. Okay, now one trader wants to verify whether this claim still adequately describes the standard deviation of the contracts. Okay, so he collected for that purpose, he collected weekly return data for 24 weeks. Okay, so here he collected 24 weeks data and measured the standard deviation. Okay, so again he measured the standard deviation, the measured standard deviation, and he found from the data it is not 0.4%, it is 0.38% actually. Now determine if the more recent standard deviation is different from the historical data. Okay, hope you people understand the question. Okay, I can again write the, not I'm going to write the question, I'm just discussing the question actually. Okay, so first let's start. We are given actually standard deviation is 0.4%. Okay, the historical data shows that the standard deviation is 0.4%, and a trader collected 24, a sample of size 24, and with the help of those 24 data, he has estimated the standard deviation is 0.38%. Now he want to verify whether these two are like same or not. Okay, so the first step is to uh, construct the null hypothesis and the alternative hypothesis. So the null hypothesis is like what? Sigma square is 0.16. Okay, because the standard deviation is 0.4%. So that means the sigma square is 0.16%. Okay, so the sigma square is 0.16% against the alternative hypothesis is what? Sigma square is not equal to 0.16%. He want to check, na? He want to check whether uh, this claim still adequately describes the standard deviation of the contract. That means the historical and the current are same or not. So it is either 0.16 or not equal to 0.16. So the next step is to uh, like uh, we use the statistic. So the statistic, suppose x square or chi square we have used here. Okay, so let's write it cal or calculated. Okay, so this is what? N minus 1 n square upon sigma square. Okay, we can write n minus 1 s square upon sigma square. We are given s square, n is also given, sigma square is also there. So under h, okay, this is under h naught already. That means the value of sigma square taken in this statistic is 0.16. Okay, so just we need to solve this. And after solving, we will find it is 20.7575. So the calculated value is 20.7575. Okay. Now, since we are like n equal to 23, 24 is there actually. Okay. So the degree of freedom is n minus 1. So the 23 is there. So the critical value, we need to like see the critical value from the table. So the critical value is like chi square with n minus 1, 23 degree of freedom at, since t distribution and z distribution are t distribution and z distribution are like symmetrical in nature. But now we are discussing about the chi square. Chi square is not symmetrical in nature actually. Okay, let me draw a curve actually. Kind of this curve, maybe any kind of curve is there, but suppose this is the curve. So here like this point and this point. Okay, so we have suppose this is alpha 1, this is alpha 2. So the alpha 1 plus alpha 2 equal to alpha, and here the value of alpha is what? We are given alpha equal to 5%, that is 0.05, or alpha equal to 0.05. Okay, so if you can see, you will find it is chi square at 1 minus alpha point, and this is chi square at alpha point. Okay, if we can like alpha and 1 minus alpha is there, and this probability is 1 minus alpha. Okay, and this property alpha 1 plus alpha 2, the probability, the sum of the probability of alpha 1 alpha 2 is alpha. Okay, so the critical value, is chi square alpha at 23 degree of freedom. Okay, at the lower value 1 minus alpha, that is 0.975. If you can see the table, you will find out like it is 11.689. Okay, and if in case you will find 0.025, then you will find it is 38.076, and we have calculated 20.7575. Okay, so obviously 25.75 is like somewhere here. Okay, so that means what? So that means it is not lie in the critical region. It is like beyond the critical region, or not in the critical region. Okay, so that is in acceptance region. So we can like say that. So chi square calculated lies within the acceptance region. So we fail to reject the null hypothesis. So that means the past record and the current record are like same. Okay, so that means we fail to reject. That means we accept the null hypothesis. If we can say, then sigma is square equal to 0.16. The same trend is observed till date. That is okay. Now, up to this point, we are performing the testing, a parametric test actually, because we have distributions, we have parameters. Okay. Now we have one more testing, that is non-parametric test. Okay. So this is like termed as test for the population distribution. Up to this point, we have discussed about test for the population mean, the difference of population means. We have also test for the population variance. Okay, now we will test for population distribution. Like we have one data and we have one claim whether this data come from this distribution or not. Okay, so this can be like termed as non-parametric test, and it has a very special name, which is called like goodness of fit test. Goodness of fit test. Okay, so like testing the significance of the discrepancies between the experimental values and the theoretical values obtained is called the testing for goodness of fit. So let me write like testing the significance. Sorry. Testing the significance of the discrepancies between the experimental values and the theoretical values obtained is called testing for goodness of fit. Okay, so this is called the goodness of fit. Also, like let me write it in remark form. Like the goodness of fit test is a non-parametric test. Okay, is a non-parametric test. Also, the goodness of fit test is used for discrete and continuous type of distribution both. So that means what? So the like the goodness of fit test is used for discrete as well as continuous distribution. Okay, so doesn't matter the nature of the distribution, we can use the goodness of fit test. Okay. Uh, okay, we have a question related to the goodness of fit. Okay, like we have a data actually first. So let me write the data first. The question is like the lifetime, okay, the life length of an electrical component. We have an electrical component that is a light bulb, okay, and the lifetime follows the exponential distribution. So let me write the question here. Like we have a lifetime. Suppose it is denoted as T. The lifetime of an electric bulb follows the exponential distribution with parameter 0.005. Okay. Now we are given a data. I've written the data. Like I'm writing data after some time. Now we need to test that the data represents a random sample. Test that the data represent a random sample from exponential distribution with parameter 0.005 at 0.01 level of significance. That means alpha equal to 0.01. Okay, so we have data. Okay, and with the help of those data, we need to test whether this data represents a random sample from the exponential distribution with the parameter 0.005. Okay, so now we are going to test whether the data comes from the distribution, the aforementioned distribution or not. Okay, so the data is actually like this. Like we have a burning time. Okay, we use a different color for the data. Uh, okay, so we have a burning time actually. That means functioning time. The number of light bulbs. Okay, so the burning time is like in interval form 0 to 100, then it's 100 to 200, then it's like 200 to 300, and then more than 300. Okay, so we have data in this format. Now the number of light bulbs is like 47, it's 40, it's 35, and it's 28. Okay, we have this data. We have actually 120, 150. The number of data is actually 150 here. Okay, so now we need to test. Okay, sorry, actually I haven't described the test statistics for this. No? Yes, I'm just discussing about the goodness of it, but I haven't described the how the test statistics is defined. Okay, we will define here. Okay, okay. Now for the test statistics. Okay, so under this condition, like the test statistic, like suppose d square is summation I from 1 to k theta. It's observed minus expected frequencies, the difference, the square of the difference of the observed and the expected frequencies divided by the expected frequency. Okay, here like OI is the observed frequency. These are the number of light bulbs are the observed frequency. The expected frequency is like defined as n. That means the total number of sample size multiplied by the pi. Pi is the probability within the related to that class interval, that class. K is the number of classes. Here we have 0 to 100, 100 to 200, 200 to 300, and more than 300. So there are four classes here. Okay. And pi is the probability related to the ith class. Okay. So we have calculated all the things. Okay. So this we are given like n equal to 150. Okay. We have also given lambda equal to 0.005 is there. Lambda equal to 0.005 is there. Okay. And pi is the theoretical probability that we have already defined. So let's solve this question. Okay. So first one is like what? We need to calculate the theoretical probability. So this one is like P1. P1 is what? P1 is probability related to the class interval 0 to 100. So it is what? 0 to 100. We are already given, we need to check na? This data come from the exponential distribution. So let's lambda e to the power minus lambda x dx. Okay, this can be solved easily. Okay, so 0.395 after solution, 3935 actually, 35 is there. P2 is like again it's 100 to 200. It's lambda e to the power minus lambda x at lambda equal to 0.005. Okay, and this can be like 0.2386. Now P3 is like 200 to 300. Lambda e to the power minus lambda x dx, and after solution we will get 0.1448. And the last one is the fourth group P4, which is 300 to infinity, lambda e to the power minus lambda x dx, and this is 0.2231. So we have like theoretical probability. Now we need to calculate the expected frequency, because expected frequency here EI is n into pi, and n equal to 150, and pi we have calculated. So sorry. So we have like even. I can write here. Okay. This I can write here. Yeah. So even is what? Even is like 0.3935 multiplied by 150. So just when we multiply, we will find it is 59.02. Okay. Again, P2 into 150 is like 35 upon 79. Then 21 upon 72 is there. And then 33 upon 47. Okay. Also, just please keep it mind, like it is 150. Okay. We can perform this test statistics when we have like summation of observed equal to summation of expected. So the summation of observed frequency must be equal to the summation of expected frequency. Okay. Then in that scenario, we will perform this test. So we are these data, these values is there. Okay. Uh, then expected value is there. And then what? Then if you can add these number, now you will find 150 actually. You will still find 150. The summation of the expected frequencies, 150. Now the degree of freedom. Degree of freedom is k minus 1. So k is 4 here. So it is 3. Okay. Now we can write this in the table actually, like observed minus expected whole square. So like 47 minus 59.02 is actually minus 12.02, and the square is like we can like use the value square. Okay. So it is 144.144.4804. Okay, I'm writing actually. I've already written these things. These are like very tedious. And then it is like 17.7241 is this. It's 176.3584. And the last one is 29.9209. Then we will divide this OI minus EI whole square divided by EI. Then we will find like divided by EI. So then we will find like it's 2.440. Okay, this is like 0.4952. This is 8.1196. And the last one is 0.8940. Okay, so from here, uh, degree of freedom is this. Okay, so the summation. Okay, let me write like this. So like d naught square, that is the calculated value. Let me write it d cal. The calculated value is summation of OI minus EI whole square divided by EI. And just we have already written all the values in the table. From there, we can take and solve and find out that it is 11.5, sorry, 95 actually is there. 11.9568. Okay, so this is the calculated value. Now from the table, since it follows the chi distribution, chi square, the critical value at 3 degree of freedom at 0.01 level of significance is actually like 11.341. Okay, so here you can see like it is 11.341. Obviously, this is beyond the like d square calculated is greater than chi square, the critical value actually. So this implies what? This implies like we reject the null hypothesis. Okay, so we reject the null hypothesis. So this is how we will perform these things. Okay, we have more topics actually to cover here, like the testing regarding the contingency table is there. Okay, that for that we have one extra session. Maybe the session will schedule tomorrow at the same time after 6 p.m. onward. Okay, if it is, then you people definitely get the notification. If not, then we will solve some other day. And now we have one some questions actually. Okay, so let's solve some questions related to the topic. Here, like we have one more question. Question is like perform a one sample t-test. One sample t-test. Okay, using the following statistics. So up to this point, anyone have any doubt?
No, sir.
Okay then. So we are given like the value of n is 5. The x bar is given like 3.871. Okay, the s is given like 0.679. Okay, we need to test the null hypothesis. The null hypothesis is given like mu equal to 5. Okay, versus the alternate hypothesis is mu is not equal to 5. Okay, at we have a level of significance also there. Okay, the question is like we need to perform a test and we have some like options actually. The first options is like x bar is given like accept at a 5% level or accept at a 1% level. Okay, so accept at 5% and accept at 1%. The B is like accept at 5% level of significance and reject 1% level of significance. The third one is like reject at 5% and accept at 1%. Okay. And the last one is like reject at 5% and also reject at 1%. Okay, so that means here like option B is like never going to be true actually. Accept at 5% and reject at 1%. It is not possible in any cases. Okay, so this is totally like not possible. Okay, the rest three are there. We need to check which one is the true for the given statistic for the this hypothesis. Okay, now we have test statistics is there. So let's use the color. So we have discussed like the T is defined as x bar minus mu upon S by root n. Okay, we are given the values actually. X bar is what? 3.871. 3.871 minus mu is actually 5. 5 divided S. S is actually 0.679. 0.679 and divided by n is here 5. So it is under root of 5. So we need to just simplify this actually. Okay, again a calculation. So after calculation, we will get minus times of 3.71. Okay, so we have a T statistics. Okay, we have statistics or we have a calculated statistics, which is minus times of 3.71. Now, now at since we have n equal to 5, so the degree of freedom will be what? So the degree of freedom is like n minus 1. So that is equal to 4. Okay. So degree of freedom is 4. Now the 95% CI for the test statistics T is under H naught is it is, if you can understand with the help of the graph. Okay. So this is like minus times of 2.776 and 2 point, sorry, 776. Okay, these are the two values at 95%. Okay, so this is 0.05 or 95% of the data is there. So at 0.5% of significance, this is the t value. Okay, let me write it t1. Now this is t2 actually. This is minus t2, and at 99% confidence limit, the value of t2 is like minus time by 4.604. It is 4.604. Okay, and this is actually 99%. That is 1% level of significance or 99% confidence level. Okay, so this, and our value is what? Our calculated value is minus times of 3.71. So that must be lie within here. This is minus times of 3.3.71. Okay, so this is the calculated value. This is the T calculated. Okay, so for 95% confidence or for 5% level of significance, this value is rejected, the H naught is rejected. Okay, so that means what? Like reject at what? 5%. But when, because for 5%, this value lie in the critical region. But for 99% confidence interval or for 1% level of significance, this value lie within the range. That is within the acceptance range. And accept at 1%. So from there, we can like understand. Okay, we have like question and we can understand. So reject at 5% and accept at 1%. So that is option C is the right one. Okay, reject, this test is rejected at 5% level of significance, but the same test is accepted at 1% level of significance. Okay, so this is how we solve this question. Okay, we have like one more question actually. Like we are given a mayonnaise producer claims that, I'm not writing the question, I'm just telling the question and then writing the solutions. Okay, so a mayonnaise producer claims that the mean weight of mayonnaise in a jar is 230 grams. Okay, so that means what? We are given the mean, he had claimed, so the population, so he had claimed the mean weight of the mayonnaise jar is 230 grams. Okay, now a random sample of 8 jars. So that means we have taken n equal to 8. The sample size is 8. A random sample of 8 jars is selected and the weight of mayonnaise in each jar is determined. We are given 8 values actually. I'm writing the sample. So the values are like 220 grams, 228 grams, 232 grams, 219, 221 grams, 223 grams, 230, and the last one is 229 grams. So we have 8 samples, okay, from like the mayonnaise jar. Okay, and we have calculated the weight and we have found these values. Okay, now the result are given. Now assume the weight of mayonnaise in a jar is normally distributed. So that means xi follows normally distributed with mean has already we are given 230 and variance is unknown. So we have assumed sigma square. Okay, now we need to test at the 5% level of significance that the mayonnaise producer's claim is true or not. Okay, so we are given alpha equal to 0.05. Okay, so I hope you people understand the question. The question is already we are given the sample for unknown. We need to check the population mean. We need to test the population, test for the population mean when sigma square is unknown. Okay, so the test statistics again. The first one is like we need to calculate the X bar actually. We are given the samples actually. So I'm not like going to calculate the X bar. So X bar is like what? Summation of Xi divided by 8 because we have 8 Xi's is there. 220, 228. These are summation and then after summing we will get 1802 divided by 8 and we will find 225.25 grams. Okay, so the sample mean is 225.25 grams. Okay, now the population mean, the claim for the population mean by the manufacturer or the producer is 230 grams. So S, okay, now S square is what? S square is like 1 upon n minus 1 summation of xi minus x bar whole square. From there on, you can solve and you will find the s square is like 25.6, somewhat this point. Okay, so the s is like 5.06. Now our h naught is mu equal to 230 versus h1, which is mu is not equal to 230. We need to check this. Okay, now the degree of freedom is n minus 1, which is equal to 8 minus 1 equal to 7. Okay, So our t value, t calculated value is what? X bar minus mu upon s upon root n, which is x bar is already there, 225.25 minus 230 upon 5.06. S is 5.06 divided by root of 8. Just after solving, we will get P calculated values minus times of 2.65. Okay. Now the critical value. The critical value is like T calculated at 7 degree of freedom at 0.05 level of significance. This value is actually 2.365. Okay, so let's again draw a curve, the T table. Okay, the T table is symmetrical in nature. So we have calculated 2.365. So it's suppose here 2.365 and here it is minus 2.365 and our calculated value is minus 2.65. So obviously that value lie somewhat here. So minus 2.65. So that is the critical value belongs, sorry, yes, that is the calculated value belong in the critical region. So that means we reject the null hypothesis. Okay. So thus what? Thus the null hypothesis is rejected. I hope this is clear because we have calculated the value. That calculated value lie in the critical region, and the critical region is the region of rejection in which the null hypothesis is going to be rejected. So we reject the null hypothesis. So I hope these are like simple. We Is there any problem? Anyone have any doubt?
No, sir.
Okay. So if there is no problem, then I think we can conclude our session here. So let me first stop the recording.